Hello, and welcome to the Bleed Air System lesson in the PMDG 737 Next Generation Groundwork from Angle of Attack. This lesson will cover the following topics: bleed air description, application, and sources, pneumatic manifold, engine-supplied bleed air, APU-supplied bleed air, and ground air connection. Bleed air system controls and cockpit indications will be discussed progressively as we move along in this lesson. Bleed air is compressed, highly pressurized air that is very hot. It's used to power certain aircraft systems that require energy from pressurized air as opposed to fuel or electricity. Many different aircraft types with different engines rely on bleed air for their operation, from turbopropellers all the way to turbofans. The temperature and pressure of bleed air varies a lot depending on where it's extracted from. On average, it may be pressurized to 40 psi and as hot as 250 degrees Celsius. Bleed air may also be referred to as pneumatic power. Specifically on the 737 NG, bleed air is used to power the following aircraft systems: Engine 1 and 2 start systems, air conditioning and cabin pressurization, Engine 1 and 2 cowl anti-ice systems, wing anti-ice systems, water tank pressurization system, hydraulic system A and B reservoir pressurization system, and a few other minor elements also rely on bleed air, such as air temperature probe aspiration systems or nitrogen gas generation, among others. Engine start systems rely on bleed air to turn the high-pressure N2 rotor when the engine start switch has been placed in the ground position. Engine and wing anti-ice systems also rely on bleed air to prevent icing formation and buildup, which could lead to rough aerodynamic surfaces and eventually loss of lift. The air conditioning and cabin pressurization systems rely on bleed air to supply and recirculate air through the cabin. All these systems are covered in the engines, ice protection, and air conditioning lessons, respectively. As we can see, there are many aircraft systems that rely on bleed air for their operation. Let's discuss where all this power is obtained from. Pneumatic power may be provided by any of the following sources: Engine 1 bleed air system, Engine 2 bleed air system, Auxiliary Power Unit or APU bleed air system, Ground Power Unit GPU air connection. Engines are the primary source of bleed air on the 737 NGX. Bleed air from all four sources is ducted into a pneumatic manifold system that collects all this air and essentially acts as a giant pool. Valves on the pneumatic manifold control bleed air flow into the respective aircraft systems. These valves are operated individually by each aircraft system. For example, when the wing anti-ice switch is placed in the on position, the wing anti-ice valve opens and air from the pneumatic manifold starts flowing into the anti-ice system. In order to provide system redundancy against any possible pneumatic duct pressure failure, a bleed air isolation valve divides the pneumatic manifold into a left and a right side. An isolation valve switch in the forward overhead panel controls the manifold isolation valve and has three positions: open. Right and left sides of the bleed air manifold are connected. Auto. The valve is opened and closed according to specific aircraft operations. Close. Right and left sides of the bleed air manifold are isolated from each other. The following systems and interfaces are linked to the right side of the pneumatic manifold: Engine 2 bleed air system, Engine 2 start system, ground pneumatic connector, right air conditioning system, right wing anti-ice system, hydraulic systems B and standby reservoir pressurization, and isolation valve. Similarly, the left side of the manifold relates to the following systems with bleed air: Engine 1 bleed air system, Engine 1 start system, APU bleed air system, left air conditioning system, left wing anti-ice system, hydraulic system A reservoir pressurization, total air temperature TAT probe, water pressurization, and isolation valve. It's not necessary to memorize what system is associated to what side of the pneumatic manifold. To summarize the important bits, we must emphasize that the ground pneumatic power connector is linked to the right side, and that the APU bleed system is linked to the left side of the pneumatic manifold. The Engine 1 and 2 bleed air systems are associated to the left and right sides, respectively. There are two duct pressure transmitters, one for the left side of the pneumatic manifold and another for the right side. Each transmitter provides indications to duct pressure pointers in the forward overhead panel. Differences between both pointers are permissible as long as there is sufficient air for cabin pressurization. The minimum value is 18 psi. Moving on, we'll now talk about each individual source of bleed air on the 737NG. Let's start with Engine 1 and 2 supplied bleed air. The engine bleed air system supplies pressurized and regulated bleed air from the 737NGX engines into the pneumatic manifold. Even though engines are very thoroughly discussed in their related lesson, we're going to briefly mention a few general aspects of how an engine works. The fan sucks outside air into the engine. After that, the air passes through a series of low and high pressure compressors that increase its temperature and pressure. Following compression, air is mixed with fuel and ignited in order to finally pass through a series of turbines that turn the respective shafts in the engine and thus turn the fan, causing a forward pushing force or thrust. A part of the air in the compressor section is extracted and ducted out of the engine. This is high-pressure, high-temperature bleed air. Technically, bleed air is extracted from the 5th and 9th stages of the engine high-pressure compressors. In some engine scenarios, such as when there's a high pneumatic demand from the aircraft systems and the engine is running at idle power, bleed air from the 5th stage is not enough to supply the required demand. In this case, the pneumatic system commands bleed air extraction from the 9th stage of compression automatically by means of a high-stage valve. Each stage of compression has a check valve that controls the flow of air between the compressors and the engine bleed air manifold. Just like the pneumatic manifold in the 737NG fuselage, there is also an engine bleed air manifold that essentially is a pool of bleed air collected from both compression stages. The 5th stage check valve prevents 9th stage bleed air from entering into the 5th stage bleed air port. There is a bleed air pressure regulator and shutoff valve, which we'll call PERSOV, that is controlled by a bleed air regulator, or bar. The PERSOV essentially performs the following functions: bleed air pressure regulation to a nominal value of 42 psi, bleed air temperature limitation to about 235 degrees Celsius by means of a thermostat and pre-cooler, and bleed air shutoff. The engine bleed air switches are located in the forward overhead panel and have two positions. On opens the related engine bleed air shutoff valve when engines are running, and off closes the related engine bleed air shutoff valve. Bleed air temperature is cooled in a cross-flow heat exchanger referred to as the pre-cooler. Ideal bleed air temperature should be between 199 degrees Celsius and 229 degrees Celsius, and it is achieved by exchanging heat between cool engine fan air and bleed air. An over-temperature mechanism protects the pneumatic manifold from receiving bleed air that is too hot. The threshold temperature is 254 degrees Celsius, after which, if an overheat condition is detected, the bleed air shutoff valve is closed and the cockpit bleed trip off light comes on. Similarly, if bleed air pressure and an overpressure condition is sensed, the same light illuminates. When a trip-off condition occurs, the bleed air shutoff valve is closed irrespective of engine bleed air switch position, and then increases beyond 220 psi. The bleed trip off light may only be extinguished by pushing a trip reset button, located in the middle of the air conditioning panel. Previously in this lesson, we talked about the isolation valve and that when it's in the auto position, it isolates or connects both sides of the pneumatic manifold according to specific aircraft conditions. It's time to discuss this more specifically. When the isolation valve switch is in the auto position, the system closes or opens the isolation valve according to the following logic. If both engine bleed switches are in the on position and both air conditioning packs are in the high or auto position, the isolation valve closes and both sides of the pneumatic manifold are isolated from each other. If either engine bleed switch is in the off position or either air conditioning pack is in the off position, the isolation valve opens and both sides of the pneumatic manifold are connected. Air conditioning packs are comprehensively discussed in the air conditioning lesson. The beauty of this feature is that when there is a malfunction in one or two engine bleed systems, the working engine bleed system may supply bleed air to both sides of the pneumatic manifold, and therefore to the components that are connected to the left and right sides altogether. In case there's any bleed air leak in the engine bleed air ducts, a wing body overheat light illuminates in the cockpit air conditioning panel. A leak is sensed with overheat detectors that activate when hot bleed air is leaking. Because the wing is generally very cold because of the cold fuel in the fuel tanks, it's rather easy to tell when the bleed air system is malfunctioning and there's a leak. Overheat detectors are located in the engine struts, inboard leading edges, air conditioning bays, and one detector downstream of the APU. To sum up, so far we've had a look at bleed air and its importance. We've mentioned the primary source of bleed air, and we've talked about a few of the undesired conditions that may arise with bleed air operation. Our discussion about the engine's bleed air system assumed that both engines were up and running under normal conditions. However, what happens during flight phases where bleed air is required but engines are turned off and engine bleed air is unavailable? As we mentioned before, two more sources of bleed air are available. Neither of them is as important and fundamental as the engine bleed air system, yet both may perform most of the functions to supply aircraft bleed air demand. Let's start by talking about the APU and its role in bleed air systems. The Auxiliary Power Unit, APU, is extensively discussed in the 737NG APU lesson. Briefly speaking, the APU is a gas turbine in the aft section of the fuselage that's capable of providing electrical and pneumatic services to the aircraft on ground and in the air. Even though the APU is capable of starting up and providing electrical power to the aircraft all the way up to 41,000 feet, it may provide pneumatic power or bleed air only up to 17,000 feet. On the ground, there's no limitation as to the pneumatic capabilities of the APU. The APU does not power all the systems that require bleed air we mentioned earlier in this lesson, such as the anti-ice system or the hydraulic reservoirs. It only supplies bleed air to the engine start systems and the cabin pressurization and thermal control. Just like with the engines, the APU has an APU bleed air duct that collects the extracted bleed air from the APU bleed air valve and ducts it into the aircraft's pneumatic manifold. There is no pressure indication for the APU duct. However, as we mentioned before, the APU bleed air flows into the left side of the aircraft pneumatic manifold, meaning its duct pressure can be obtained with the duct pressure indicators we also discussed previously. In case the pressure regulating function of the APU fails and excessive bleed air is ducted into the pneumatic manifold, an APU pressure relief valve protects the pneumatic manifold duct from rupturing by relieving bleed air overpressure. Any pressure under 75 psi is normal. When the pressure exceeds this valve, the APU pressure relief valve opens and only closes back once pressure has dropped below 65 psi. The supply of APU bleed air is not directly controllable. In the case of engine-supplied bleed air, the thrust lever position has a direct incidence on the temperature and pressure of bleed air. If both the APU and engines are supplying bleed air to the pneumatic manifold, there's a high chance of it rupturing. The ducting is relatively thin, and therefore, caution must be exercised when selecting multiple bleed air sources for pneumatic power. A dual bleed light in the forward overhead panel is available to protect the aircraft from this condition. It illuminates when either or both engines and the APU are supplying bleed air to the pneumatic manifold at the same time. Either the engine 1 bleed switch must be on and the APU bleed air valve open, or the engine 2 bleed switch must be on, the isolation valve open, and the APU bleed air valve open. The immediate action following a dual bleed light is to put the thrust levers to the idle position during a dual bleed condition, such as after engine startup. Once the engines have started up, the APU bleed air switch must be turned off. Going back to engines, when bleed air is extracted from them, part of the air that enters the fan is no longer producing thrust. Instead, it is being ducted out of the engine for pneumatic power. This means that the engine would not be delivering its maximum thrust capacity, and there are situations where this condition may be conflictive, such as during takeoffs from short runways. If you picture a hot day at a short but high runway, and the engines are not producing their maximum thrust, the takeoff distance may be increased by a huge factor. Huge enough that there will be an enormous chance of a runway excursion if the takeoff is attempted. Under these cases, flight crew on a 737NG may perform a bleeds-off takeoff. In this procedure, both engine bleed air switches are turned off. Therefore, all the air that enters the fan is virtually capable of producing that extra thrust we need to take off in the marginal conditions we discussed previously. In a bleeds-off takeoff, the APU bleed air is responsible for powering the pneumatic system. Therefore, the APU must be running and the APU bleed air switch must be in the on position. Once the airplane is airborne and the takeoff flows have been completed, the APU may be eventually turned off and the engine bleed air switches turned back on. Keep in mind that when only the APU is powering the pneumatic manifold, air conditioning, pressurization, and engine starters are the only bleed air demanding components that are available. Having talked about the APU's pneumatic capability, let's move on to the third available source of bleed air on ground. When both engines are off and the APU is temporarily unavailable, pneumatic power may be obtained from an external source of bleed air. A ground pneumatic connector allows an external ground power unit, or power cart, to supply compressed air into the pneumatic manifold. Similar to the engines and APU, this ground connector is also attached to a check valve that prevents flow out of the manifold. As we mentioned before, the engines supply bleed air to both sides of the pneumatic manifold. The APU supplies bleed air to the left side, and the external air connection is coupled to the right side of the pneumatic manifold. The ground external air connector and its check valve do not have any form of bleed air pressure or temperature regulation. Instead, the ground power unit or power cart that supplies the external energy is responsible for delivering adequate temperature and pressure bleed air. A placard near the external pneumatic connector sets the external bleed air limitations. They are: maximum external bleed air temperature is 232 degrees Celsius. Maximum external bleed air pressure is 60 psi. Only two conditions must be met for external power to be provided. The flight crew must ensure these. The battery power must be on, and the air conditioning packs must be off. Both these items are explained in the 737NG electrics and air conditioning lessons, respectively. The bleed air system is surely easy to operate. However, it may take a few study sessions to fully understand how everything works in it. In this lesson, we discussed what bleed air is, where it's obtained from, and how important it is for safe operation of the 737NG systems that rely on pneumatic power. Caution must be exercised when using the different sources of bleed air. During all operations of the pneumatic system, the wing body overheat and bleed trip-off light must be constantly monitored for malfunction. Any form of bleed air overpressure or overtemperature may break the pneumatic manifold apart. When in doubt, always adhere to standard operating procedures and the aircraft flight crew documentation. This lesson covered the following topics: bleed air description, application, and sources, pneumatic manifold, engine-supplied bleed air, APU-supplied bleed air, ground air connection. Stay tuned for the following lesson on the 737 air conditioning system. Until then, throttle on.